for fusion for producing nuclei by similar projectile and target nuclei. And this contradicts to the experiment. Here is shown schematically in the eta R plane how the system moves in these adiabatic models. Here is the entrance channel, and here you have the touching point, and then the system moves to some more symmetry. Eta 0 is a symmetric fragmentation, and some part goes out, and this is called quasi-fission, because no compound nucleus is formed. And the small rest goes then down and fuses here in the internuclear distance. So you can see the dynamics schematically in the adiabatic models. Here I've shown you some potential energy for the system calcium plus curium. This is from Zachariah in Dubna. Here is the eta coordinate, and here is the relative coordinate. And you come here in with a certain fragmentation, and then you move here to more symmetry, and because here the barrier is smallest in this adiabatic model, and then you move to the compound nucleus. In opposition to this model is the so-called dinuclear system model, which uses diabatic potentials. And these dinuclear systems assume that the fusion is given by transfer of nucleons between the nuclei. Now you can think on the lunch. You have a smaller nucleus and a larger nucleus, and the larger nucleus eats up the smaller nucleus by transferring the nucleus, and then you end up by eta equal 1 to a fused system. And this, for this, you need a diabatic potential which hinders the system to smelt together. So the system touches and can nothing do as transferring nucleons and coming then to the compound nucleus. It's a completely other type of motion. And here is shown how this looks schematically. You have again the entrance, and some part of the wave function goes to the quasi-fission and fissions again, and some small part goes to larger values at eta to the fusion and the touching configuration. If you remember on this adiabatic picture, it's a completely other mechanism. Here is shown the iron plus plutonium system going to 120, and this is the potential. Here is the relative coordinate. Here is the mass asymmetry coordinate, essentially, is the mass number shown. And you come here along, and this is a diabatic potential. You cannot go further on. And then you go to the side, and you have a small barrier to fuse the system. And this is a dinuclear system concept. We have calculated with this dinuclear system concept fusion cross-sections, and here I've shown you probabilities for a reaction with a lead target. These are cold fusion probabilities. They go from 10 to the minus 1 to 10 to the minus 10. If you go from 102 to 120, and here above, with some larger probabilities, is this hot fusion, where you have calcium plus some rest nucleus. This dropping of these probabilities is easily understood. In this direction, if you take the lead target, the system gets more symmetric, and therefore the barrier gets, for the inner barrier for fusion gets always larger and larger, and so the probability goes down. Now, if the nucleon zip all in this diabatic potential at high energies, they like to drop down, and they drop down through the adiabatic potential with time. So this diabatic potential keeps not a long, long time. And we have taken a characteristic relaxation time, tau, for the shape degrees of freedom for the system, and we calculated the diabatic potential as function of time. You have an occupation number, n alpha diabatic, which depends now on time. And here you have the adiabatic occupation. And for this change of the diabatic